A single photon left a galaxy before humans existed. It hits your eye tonight and still carries a clean timestamp. The immediate takeaway is simple. Some signals survive the universe almost unchanged. That is why measuring anything out there is possible. We are not guessing. We are catching messengers built to last. So the question is sharper. Why does reality let information travel so far and stay honest? Stand on a dark ridge while the Milky Way arches overhead. By measurable, we mean nature offers stable patterns you can compare. That matters because comparison turns wonder into numbers you can test. Patterns become tools when they repeat and stay consistent across time. Mechanically, measurability needs three things: a signal that can travel, a rule that does not drift, a detector that can be calibrated. The universe gives us all three more often than chance. Light, gravity, and particles move information across absurd distances. Symmetries keep the rules steady, while detectors translate tiny nudges into data. Example in real terms: the same hydrogen line appears at 656 nanometers in labs. It appears stretched in distant galaxies, but the pattern stays precise. That anchor lets redshift become distance, and distance become history. Bottom line, measurement starts when patterns persist beyond your backyard. A lighthouse sweeps across black water, and sailors time the flashes. Light in space does the same job, only faster and cleaner. Here, light is both ruler and clock in one beam. That matters because one invariant speed links seconds to kilometers effortlessly. The core rule is famous. In vacuum, light moves at one constant speed. So time and distance trade places, using simple multiplication with c. Photons also carry color, which encodes motion through Doppler shift precisely. String a spectrum through a prism, and speed turns into tint. Now a quick check. 1 light second is about 300,000 kilometers. The moon sits a little over 1 light second away. A supernova in Andromeda is 2.5 million light years. Its photons traveled that long, yet still preserve their spectral lines. Net result: light makes space and time commensurable, so clocks meet rulers. Picture ripples on a pond that never fade, while stones still move. In physics, those ripples are conserved quantities that do steady bookkeeping. Conserved means the total never changes, despite complex internal trades. That matters because perfect bookkeeping lets you trust what leaves a source. The engine is symmetry. When laws look the same in time, energy is conserved. When laws look the same in space, momentum is conserved. Spin symmetries guard charges, which stabilize atom behavior across eons. With these guards, signals do not lose identity while traveling. Example in numbers. Type Ia supernovae convert about 1.4 solar masses. Their energy release is about 10 to the power of 44 joules. Because the process is standardized, peak brightness scatters by a small margin. That small scatter makes them excellent distance markers across billions of light years. So the picture is, symmetry locks the ledger, and measurement stays honest. Zoom out past our galaxy into a fog of faint threads. Between galaxies sits gas so thin, a vacuum looks crowded beside it. Measurability needs windows, where messengers pass through with little interference. That matters because clutter blurs signals, while windows keep information crisp. Space is kind here. Radio waves cruise through dust, while optical light threads gaps. X-rays trace hot plasma, and microwaves cross the whole observable sky. Even neutrinos and gravitational waves bring stories, skipping matter almost entirely. The mechanism is simple to picture. Different wavelengths scatter differently, depending on particle sizes in the way. Long waves dodge small grains, short waves slam into dense clouds. Astronomers match messenger to medium to keep signal losses small. A concrete case helps. Cosmic microwave background photons last scattered 13.8 billion years ago. We still map their tiny ripples at tens of microkelvin precision. Rule of thumb: use the cleanest window, and the message survives. There is a scale where city maps dissolve and continents look smooth. The universe has a similar scale, where lumps blur into uniformity. Homogeneous and isotropic means the big picture looks the same everywhere. That matters because averages tame local chaos and unlock global rules. The working idea is the cosmological principle, supported by wide surveys. Galaxies cluster on filaments, yet their statistics stabilize beyond big scales. Expansion looks uniform once you blur over a few hundred megaparsecs. That uniformity lets simple equations describe huge volumes at once. A grounded number helps. Beyond about 300 million light-years, density variations are small. Fluctuations are a few percent, not tens of percent like nearby. That stability lets redshift line up with distance with predictable scatter. It also makes background maps statistically interpretable, not a one-off oddity. Net result, sameness on large scales makes distant comparisons actually fair. Walk into a quiet dome where a mirror stares at cold stars. We need cosmic yardsticks that come with built-in labels. A standard candle has a known brightness, so distance dims it predictably. A standard ruler has a known length, so angles shrink with range. That matters because you cannot touch galaxies, but you can compare. The chain begins nearby. Parallax sets the first rung, using Earth's orbit as baseline. Cepheid variables tie periods to brightness, stitching kiloparsec distances securely. Type Ia supernovae leap to gigaparsecs, keeping the scatter surprisingly tight. For rulers, galaxy clustering leaves a frozen sound horizon. The baryon acoustic scale sits near 150 megaparsecs. Astronomers spot that bump in surveys, then turn angle into distance. Tiny test, ask two tools the same question, and watch agreement form. Bottom line, candles and rulers turn the sky into a calibrated ladder. Set a metronome on a lab bench while lasers hum nearby. The units we use are not arbitrary decorations, they are anchored. A second is defined by cesium's tick, measured as a frequency. A meter is defined by light's path during a set fraction of a second. That matters because definitions travel while artifacts stay stuck in vaults. The method is elegant. Take a stable process in nature, then enshrine it as a unit. Build devices that count the process and share the recipe globally. Now anyone, anywhere, can rebuild the yardstick from first principles. Numbers make it vivid. Cesium hyperfine transition runs at 9,192,000,000 Hz. Multiply by light speed and distance flows straight from time. Planck's constant nails the kilogram, tying mass to quantum energy directly, so the takeaway is simple. Shared constants give civilization one ruler that never warps. A storm of signals can still mislead if your tools drift slowly. Trust in numbers comes from calibration chains and cross-checks. Calibration means comparing a device to a standard under known conditions. Cross-checks mean asking independent messengers the same question. That matters because agreement across methods beats any single clever trick. Here is how it works in practice. You observe with two telescopes, staggered in time. You inject faint test signals while a robot wiggles mirrors methodically. You track air, temperature, and detector response, then adjust the pipeline. Finally, you compare the answer to a different technique entirely. Example with stakes. The Hubble constant measured by supernovae sits near 73. The microwave background prediction lands near 67 instead. That tension persists despite heroic calibration and prompts fresh ideas. Bottom line, reliability emerges from disagreement tested hard, not from blind faith. One last image. You hold a photon that left before our species learned fire. It arrives intact because nature stabilizes messengers, rules, and comparisons. That is why the universe can be measured at all. We turn travel into time and spectra into speed using shared constants. The big picture is calm. Reliable patterns beat distance while cross-checks police our confidence. If you want more cosmic clarity, stay tuned for the next deep dive.